Hi, this is Steve Scully. I'm back with Chapter 4 of the instruction manual as it is written in the cosmos. This chapter is called the Not So Fundamental Forces. So, Section A, the Fundamental Forces. In nature, there are said to be four fundamental forces that produce everything we see: gravity, electromagnetism, strong interaction, and weak interaction. By definition, a fundamental force is causeless. However, this does not pass the sharpness test because it could be simpler to have fewer. Moreover, as previously discussed, the electromagnetic fields are the result of gravity. Therefore, electromagnetism is not as causeless as it appears. Present models are unable to link these forces together to explain any with another. However, it is possible to explain all other forces as a result of gravity, and to subsequently explain gravity as a result of the infinite nature of the universe. Section B, the nuclear forces. Strong and weak interaction are known as the nuclear forces. These are only detectable on the atomic scale. As a result of this limited range of their applicability, it is clear that neither are universal but are environment-dependent emergent phenomena. As has been established, there is a correspondence between systems of all different masses. Whether they be a star or an atom, they function equivalently. This principle indicates that the same phenomena are observable across layers. In this particular instance of the nuclear forces, the procedure is then to examine the characteristics of the forces to determine whether they are observable in the objects of the cosmos. Strong interaction is said to cause subatomic particles in the nucleus to remain bounded through nuclear fusion. Historically, nuclear fusion of atoms is thought to occur generally at the center of a star. The process of where two systems will merge to become a new system and release energy and mass in the process as shown in Figure 2. So two systems, deuterium and tritium, combine into a new system of helium, releasing a particle of a neutron and energy. Importantly, nuclear fusion is considered to involve systems such as protons and neutrons, which make up the atomic nuclei, which has previously been discussed as an approximation. Each is one system, not a conglomeration as described. If we look to the stars, we can see this very same process in action. Generalizing the process to two systems combining into a single system, into a single larger system, and releasing specifically energy and a smaller mass system, this very same mechanism exists in what is known as a supernova type 1a. This process is depicted in Figure 23 below. These are the same process, just as in nuclear fusion. For a supernova type 1a, two masses come together and the larger mass extracts energy from the smaller mass until the larger mass reaches a critical point where it supernovas, releasing a specific amount of radiant energy and pushing away the companion star after the process. When we witness a supernova type 1a, we are witnessing also nuclear fusion. All things function the same. In the case of a supernova type 1a, we do not associate the mechanics to be the result of strong interaction. Rather, supernovae are known to be gravity-driven. In other words, gravity causes strong interaction because nuclear fusion is the same mechanism as supernova type 1a. This is only reasonable from a sharpness perspective. As the result is a sharper point to the model, the conclusions are supported by logic. So here we see a supernova type 1a or two systems combine. The larger mass star becomes a giant by taking mass off of the other system, in essence. And then over time, it reaches a critical mass and explodes and ejects the companion star away and releases always a specific amount of energy, which is why it's known as a standard candle, where it basically allows us to determine the distance away that it is based on its luminosity versus its known brightness. Or did I get the... its brightness versus its known luminosity. From a similar analysis, weak interaction can also be seen as the result of gravity. Presently, weak interaction is closely associated with radioactive decay. Using the same process, which is part and parcel of each step in the step-by-step deduction of the universe's mechanics, the two forces can be connected. Once again, to see inward, we look upward. Radioactive decay can be characterized. It is the sudden and spontaneous decay of a system to a lower energy state, coupled with a release of radiation in the process. This spontaneity comes after a period of relative stability prior to the decay's occurrence. It is more prevalent in higher mass atoms, and radioactivity generally increases with mass. As a nuclear force focused on the nucleus of an atom, the same mechanism can be seen in the function of stars. While the supernova type 1a was a specific circumstance where two systems merged, if we look specifically at heavier stars pushing the upper limits of the mass of a star, then we can see the same general trend where the rate of supernovae drastically increases as star mass increases. This is because supernovae are radioactive decay. This can be considered from a pressure standpoint. When a system grows, its pressure outward is higher due to the accumulation of more and more mass in a given volume. Growth occurs due to an environmental influx of greater energy into input than energy output. As a result, when a very massive star forms, it is also very high in pressure relative to the lower mass stars that occupy the same general environment. Over the course of time, it can enter into an environment that the lower mass star would essentially, quote, feel as high pressure. And so the lower mass star is able to feed off the environment. But due to the very massive star's high pressure, it experiences the same environment as low pressure. If it is low enough, this can lead to a sudden expulsion of mass to the environment due to the imbalance being high. This then makes the environment higher in pressure while making the star lower in pressure, and so the star can become highly stable relative to its environment as balance is restored. As a result, a system such as a star or an atom is much more stable than their peers in a given environment when they are in balance with that environment's general density. Above or below equilibrium, unless the environment changes so the system is at equilibrium relative to a new environment, creates greater instability. Thus, masses furthest from equilibrium are the heaviest and the lightest, alike to infinity and zero. Balance is between them. In balance, there is stability. As supernovae are the result of gravity, so too is weak interaction. From the above analysis, where the principle of correspondence between all systems is recognized and applied, it is determined that gravity causes the nuclear forces. This improves the sharpness factor greatly, as these so-called causeless fundamental forces of strong and weak interaction are shown to be directly resultant from gravity. All right, so that's the end of the nuclear forces. So I'll go ahead and stop this video here. Next video, we'll continue with electromagnetism. We already talked about electromagnetic fields, but we have not talked about specifically how electromagnetic waves are formed. So we'll talk about that in the next video. All right, thanks for stopping by.